So hi everyone, I'm Edwin. I'm a PhD student at the University of St. Andrews, and today I'll be talking about my work, which is Bayesian Networks and their applications in modeling resilience and regime shifts. So before I get into it, I just want to give a brief outline about what I'll be talking about today. I'll start off with some context behind ecological resilience and how Bayesian networks fit into this framework. And then I'll be going through these two case studies, which has been work I've been doing over the past couple of years. The first one was something that was out of my master's project, which is Bayesian networks as a novel tool to enhance the interpretability and predictive power of ecological models. And the second one is something I'm working on just now as part of my PhD, which is a novel integration of dynamic Bayesian networks and non-additive modeling to study ecological resilience. And then I'll close up with some remarks on future work and the future direction. So ecological resilience, what is it? So the example that I like to use is this ball in the cup heuristic. So the ball at the bottom of this valley represents a system that exists in stability. And that confers a set of ecological relationships that exist in equilibrium. So if I were to physically push this ball up this valley, I'd have to, apply some force into it. And that force is essentially any form of disturbance into the system. So therefore, the ability of this ball to resist this force and disturbance and return to its original position is the resilience of this given system. And another way to think of it is that the height of this given valley is the resilience of a system. Now, it goes without saying that there's only so much of this disturbance that a system can absorb before hitting a threshold. So once you push this ball far enough to the tipping point, any small perturbation is going to be enough for it to fall into this new valley. And once it enters this new valley, into a new stable state, it's essentially a new equilibrium, which is an entirely different set of ecological relationships compared to your original stable state. So to give an intuitive example, this is an example that I like to use as well. Consider a coral reef system. In the left-hand side, that's a healthy equilibrium that is regulated by this core feedback loop between coral and the algae that live in the coral. Now, with global warming, sea level, sea temperature increases, there's only so much of this sea temperature increase that it can tolerate. So once it passes this threshold, there is a breakdown between that core feedback loop between algae and the corals, where the coral expel the algae, and you have a coral bleaching event, and that will be the new equilibrium. And it's going to be completely different from your original state because you have a loss of biodiversity, you have dead coral, you have less amounts of fish that's going to be hanging around that area. So when it comes to studying resilience and regime shifts, what are the things that we need to consider? What are the questions that we need to ask? So the first one would be, what are the dynamics that regulate stability and resilience? So I spoke about how the ball at the bottom of the valley confers a set of ecological relationships at equilibrium. But are there quantifiable metrics to this? Can we quantify these relationships? And next, how do we assess resilience? I spoke about, in abstract terms, about how the height of the valley is the resilience of the system. But again, can we quantify this from natural data? And with this quantifiable metric, can it then be applied to different domains, different systems across different domains? And lastly, how do we identify tipping points? Do tipping points emerge from natural data? These are all questions that need to be addressed when studying resilience. So how do Bayesian networks fit into this framework? Well, when it comes to the dynamics that regulate stability and resilience, it turns out that the conditional dependencies from Bayesian networks translate quite well into ecological relationships within a community. So that gives us a good, starting point to, at the very least, review the internal dynamics of a system and stability. But when it comes to assessing resilience and identifying tipping points, that's more dynamic in nature. So that would require an integration of temporal processes. And that will come in the form of dynamic Bayesian networks. So this here is going to form the premise of the talk. I'm going to start off by talking about static Bayesian networks and how they can fit in revealing the stability and resilience dynamics and the things that regulate it. And then I'll move on to talk about dynamic Bayesian networks and how they can fit in everything here. So this is the first case study. Bayesian networks as a novel tool to enhance the interpretability and predictive power of ecological models. So the aim here, I applied a static Bayesian network inference algorithm on a system with known links to test the ecological validity of the reviewed network. So if you look here, that's your typical rocky shore ecosystem. It's very, very simple. It's only a couple of species, and there's high levels of interactions, and they're well-documented links as well. So it's a perfect system to test the validity of any model that you want to test, because you already know what it should look like. And then I will then evaluate the potential usefulness of the structure of the reviewed networks through the Markov blanket as a novel variable selection tool to train predictive models. So what I'll be doing is that I'll be training artificial neural networks and generalized linear models with no variable selection and with variable selection. So to give an example, let's say I want to predict the presence of top shell. On one hand, you could essentially train a model with everything in the network. On the other hand, you can then use the Markov blanket of top shells to essentially do variable selection to reduce the number of dimensions in your predictive model. So in terms of feed methods, it's very simple. We had 50 quadrats, random sampling. We obtained individual counts for grazers. So those are the limpets and the littorinids. And then we use percentage cover for the macroalgae and barnacles. So those are the sessile species that are already established on the rock itself. So in terms of the Bayesian networks that were reviewed, the Bayesian networks reviewed specific important relationships. So here, barnacles and macroalgae, there's a strong negative link. And that makes sense because barnacles and macroalgae on a rocky shore, they represent alternative assemblages. So if you were to observe an area with high levels of barnacle, it would make sense that there's going to be very few macroalgae in that same area. Additionally, grazing relationships were captured accurately as well. So limpets generally graze on microalgae, which tend to reside in macroalgal patches or barnacle stands. So this positive relationship also makes sense because limpets will be more likely to be in areas where microalgae are present. And same for littorinids and macroalgae. Macroalgae provides some sort of refuge for littorinids to essentially act as a buffer for wave action, and also provides a little bit of food via microalgae. Therefore, there's a positive relationship here. However, we should also note that this network here represents a static snapshot of your system stability, right? Because if you were to take repetitive observations over time, this grazing relationship, for example, with limpet and microalgae, could also be a feedback loop where limpet will reduce the number of microalgae over time. Hence, there could also be a negative relationship. And the same can be said about littorinids and macroalgae, because littorinids over time can also reduce the amount of establishing macroalgae. So that's one thing to keep in mind. When it comes to training artificial neural networks with the Markov blanket variable selection, there were improvements in predictive accuracy, particularly for the macroalgae and barnacle models. That also makes sense because macroalgae and barnacles, those, again, as they confer alternative assemblages, it's reasonably simple to improve model accuracy by selecting this accurate variables when it comes to these two variables. However, for the grazer models, in terms of limpets and littorinids, they did not perform as well, even with variable selection. And we think here it's to do with missing covariates because we only measured the count and percentage cover of these 5 species. But the distribution of limpets and littorinids aren't just, they aren't just limited by the presence of other species, but also physical abiotic factors that we did not measure. So even if we were to select the variables based on the Markov blanket, you'll be overfitting essentially. And last but not least here, artificial neural networks significantly outperform our GLM models. And that's not too surprising because artificial neural networks can handle noisy, nonlinear data as they do not make strong assumptions about the underlying distribution of the data. So perhaps another thing I could have done here would be comparing the performance of artificial neural networks to, say, generalized additive models or any other type of nonlinear regression models. But that's not something I did back then for my master's. So the key takeaways here is that combining Bayesian networks and artificial neural networks, they show promise in the field of ecology. On one hand, the Bayesian networks can review ecological network structures and explain the underlying relationships between variables. And using the above information, this can then guide the training of powerful predictive models by serving as a robust variable selection tool. Now, in terms of the limitations of using the static Bayesian network inference algorithm, well, we are unable to model competition or feedback loops. And that is a pretty important limitation because when it comes to regulating a stability and resilience, these things, feedback loops are crucial when it comes to regulating stability. So that is where the next topic is going to come in, because now we're going to take it from a static Bayesian network to a dynamic Bayesian network to try review what changes and how a system responds to disturbance. So that's where we are now with the next talk, a novel integration of dynamic Bayesian networks and non-additive modeling to study ecological resilience. So as we just talked about, Bayesian networks in the context of resilience, it's good to review. It's shown promise in revealing the dynamics that regulate a system and stability, but it's unable to model, resilience dynamics or, in fact, how it responds to disturbances. So that's one of the current approaches. Another approach that's emerged is through non-additive modeling. So over here, this is a novel non-additive modeling method that was derived by Vasilakopoulos et al. In 2017. So essentially what you're seeing here is that they applied principal components on their ecosystem data to derive generic variables. And they used the coordinates of principal component 1 as a generic system indicator. So at 1, everything above 0 here represents one system state. And then you can see the transition along this axis into a new state. Once they have that, they fit a threshold generalized additive models. And those are the 2 lines that you see here. And these 2 lines essentially represent the 2 basins of attraction. And then they try to fit these predicted tipping point to show this nonlinear shift as a response to the sea surface temperature over time. So what are the colors? These are the relative resilience values. The way they do it is that they compute the relative distance between each point to the line itself and also to the tipping point. So you'd imagine that anything that's further away from the tipping point will be relatively more stable. Anything that's closer to the tipping point is going to be a lot less stable, as reflected by these values up here. So essentially what you're seeing here is a quantifiable metric of what we talked about in this sort of shift. So far, these 2 methods have been largely separate, but there's a potential integration of both approaches. Because when we think about the framework, what are the dynamics that regulate stability and resilience? Well, Bayesian networks can review internal dynamics, but we can also integrate temporal processes to see how these internal dynamics respond to disturbances. In terms of assessing resilience and identifying tipping points, this novel non-additive modeling has shown promise here as well. But also, perhaps if we combine it with, say, a dynamic Bayesian network, could we review generic features of network structure that lead to something to be less resilient or more resilient? These are clearly open-ended questions that have a lot of room to explore. So that's what I'll be doing. That's what I'm doing right now in the PhD. So what we're proposing, is a 2-step modeling process. The first part is a dynamic Bayesian Gaussian mixture Bayesian network model that was proposed by Gorch et al. In 2011. And it includes change point processes to account for the temporal structure with the aim of revealing the network structure of ecosystems and where the change points are in this time series in the internal dynamics as the system responds to the pressure. And then we'll be complementing this with the integrated resilience assessment, the IRA modeling, which we spoke about earlier, and essentially that 3-step process, which includes dimension reduction, non-additive modeling, and resilience assessment. So to contextualize this, we have the feed methods. So it's very simple. We had 10 boulders with 2 conditions. These boulders are essentially, imagine a big block that's just dominated by green seaweed. So 5 of them we're just going to leave alone. And the other 5, we're going to significantly increase the grazing pressure by adding 20 top shells. And we're going to see how this responds over time. So we collect data at 2-week intervals, 6 times in total, which gives us a sampling time of around 3 months. So this is the Bayesian network for our control conditions. So it's a very simple system right now, as I mentioned earlier. But importantly, we were able to review and recover this core feedback loop between top shells and green seaweed. And that makes sense because this is a green seaweed. It's essentially a boulder of green seaweed. That is the system. And this is regulated by the grazing relationship between top shells and green seaweed. And there's only going to be so much of this grazing pressure that it can tolerate before you have a change. But this is the important part. This core feedback loop between top shells and green seaweed. Now, in terms of the change points, we identified a change point at week 6, which implies that there's a change in species interaction from week 6 onwards. So keep in mind the simple nature of this feedback loop here. And now we can see how this changes once we add 20 top shells. The core feedback loop between top shells and green seaweed is indeed still here, but now there's additional interactions between green seaweed and fucus and top shells and fucus. What we're thinking is happening here is that once you significantly increase the grazing pressure, over time you have a huge reduction of green seaweed on the boulders, which gives space for fucus to establish, hence these extra feedback loops. And when you compare that back to the original control network, you can clearly see how it's a lot more complicated right now. And here we identified 2 change points on week 4 and week 6. So we put them side by side, you can clearly see the differences between the 2 network structures. One on the control and the other one when we significantly increase grazing pressure. So that's just a network structure, but how about the structure of the shift itself and the resilience dynamics? So that's where we can move on to the IRA model. So this is the fitted model that we have. Our system state 1 is our system states are principal components, and essentially everything above 0 represents a higher green seaweed state. And on our x-axis is just the number of top shells. So in our control condition, most of them were able to stay within the green resilient zone. And yes, there's been some increase in grazing pressure over time, but nothing significant. And here, there's one observation where there was a lot more grazers, and it passes this tipping point, falls down to the lower tractor, and then there's a great change in that gradient where it's a steeper decrease in green seaweed. So the system state, there's a slight shift in the system state. And actually, when I mentioned the change point at week 6, that corresponds to this point here. So week 6 onwards, there's that change in that grazing relationship where there's a steeper gradient. So how does it look like when we add 20 top shells? So they all start off relatively resilient here, except for this one condition. You add 20 top shells, it overshoots, and then it bends backwards to the lower fitted attractor, and then you see that change in the gradient in the grazing pressure, and there's a significant shift in the system state from high green seaweed to very low green seaweed. And if you compare it side by side here, you can really see the structure of the shift and the associated resilience dynamics. You start off resilient, and once you increase grazing pressure to a certain point, there is going to be a change in the interactions between top shells and green seaweed. And here you just clearly overshoot and then back down here. So how does this look in the context of resilience and regime shifts? So on one hand, we have a network, a dynamic Bayesian network with change points that could show essentially the core feedback loops that regulate resilience, all right? Now, we can also see where the changes are. With the change point processes, we can identify what's the point where the species interactions are changing. Now, that's very nice when you complement that with this RA model, because the IRA just simply finds out where is that point where there's a significant shift in system state. And on the other hand, the Bayesian network shows the change points where, okay, once you pass that threshold, what's changing and when is it changing and what's changing? And if we think about it back to this graph, essentially, our IRA model, the thresholds here is essentially trying to predict where this tipping point is, and it derives resilience based on the distances between your system state to the tipping point. And your change point essentially shows, okay, once you pass this tipping point, when does it start changing or what starts changing? So this shows a lot of promise. So in terms of moving forward, what am I going to do in my PhD? I'm going to be applying this framework and developing this framework on more complex water systems. I'll also be looking at much larger marine ecosystems, which with far more dimensions, so either fisheries or coral reefs. And as a curveball, we're also going to be looking at macroeconomic systems as another complex systems, because we're really interested to see how this framework can be applied to complex systems across different domains. In terms of model considerations, some things I'm considering right now is, can we extract interaction strings in the Bayesian networks? That should be doable. Next thing is selection of stresses in more complex systems for the IRA model. So obviously with our border systems, it's very simple. It's really easy to just identify, okay, our stresses are just the amount of grazers. But what happens when we move on to larger marine ecosystems, such as fisheries? It's not just going to be one stressor, right? It could be a combination of multiple stressors. So how can we essentially select the correct stressors? How do we deal with cases when there's a combination of stressors? So these are all, again, open-ended questions that I'll be exploring further in my PhD. So that's all I have for you today. I'm happy to take questions or even suggestions. Yeah, thank you.